the wave function.
The wave function.
The wave function.
If you know even a little bit of quantum mechanics, you have definitely heard of the wave function. But what is a wave function? In this video, we will answer this very question by taking a look at the postulates of quantum mechanics. Specifically, we will try to understand the wave function postulate. By the end of this video, you'll have a better and more intuitive understanding of what a wave function is and how it represents the state of the system. So, stay tuned. Now, the wave function postulate of quantum mechanics says that the state of a quantum mechanical system is completely specified by a function psi of rt that depends on the spatial coordinates of the particle and on time. Let's understand it in detail. One concept that I think is often used but rarely explained in quantum physics is that of the state. And if you want to truly understand what the wave function is, it is crucial to understand what we mean by the quantum state of a system. You see, in classical mechanics, the state of a particle is described by its position and momentum. We are interested in position and momentum specifically because not only can you express other important properties in terms of these variables, but also because they help you to predict how the system would evolve over time. So the state of a classical system is, in essence, just the position and momentum, as knowing these two variables lets you determine all you'd ever want to know. Note that up to now, we have been talking about classical non-quantum physics. In the quantum realm, it's not so simple anymore. For instance, we know from experiments that properties of quantum particles are probabilistic. You can't be sure of the position of your particle. Sometimes, all you can say is that a particle has 70% chance of being here and 30% chance of being there. It's first when you observe your system that you will find your particle in one of these two places. 70% of time here and 30% here. And by the way, this kind of uncertainty also applies to other observables like energy, momentum, and so on. As a result, in quantum mechanics, we don't really talk about particles having specific values for observables, but rather we talk about the probability distributions of those observables. Due to this unusual nature of the quantum world, the state can no longer be described using just the position and momentum. In order to describe a quantum state, we need something different, something more. And that is the wave function psi. Okay, so if you're with me so far, why not show your support by smashing that like button and subscribe for even more awesome content about the fascinating world of quantum. Anyways, according to the postulate, the wave function describes the quantum state, but in order to actually do what the wave function is intended to do, it has to satisfy some properties. The first property is that it must be a mathematical function of two variables, position and time. Furthermore, this postulate states that the wave function must also be such that the probability of a particle being in an infinitesimal volume dV located at a position given by a vector r at time t should be given by psi star psi dV, where dV is the infinitesimal volume of this cube. and psi star is the complex conjugate of psi. Firstly, the fact that we are using the complex conjugate hints at us that the wave functions can be complex functions. In fact, real wave functions are actually quite rare. And secondly, this property implies that the integral over psi star psi dv must be 1. See if you can figure out why. In each video, I try to give you something to think about because independent thinking is very helpful for truly understanding something. So do try to think about it. And if you're feeling bold, see if you can crack Einstein's challenge of explaining it to a 6-year-old. And I also think that it's nice to have seen this equation because you have to deal with it pretty often when you actually get into the math of quantum mechanics. It's also worth noting that this is not an exhaustive list of all the properties of the wave function, but these properties that were mentioned in the wave function postulate are unique because they tell us what the wave function itself is. Okay, now we have been talking quite a bit of theory for the last few minutes. So here are a few examples of some actual wave functions. Feel free to pause the video here to take a good look at them. You'll quickly notice that these functions are quite complex, in both senses of the word. Anyways, let's recap just a little bit before moving forward, shall we? Remember that we are interested in the state of a system since knowing it lets us predict how the system will change over time, and it also lets us deduce all physically observable quantities like energy, velocity, and so on. So it's really important to know the state of a given system. But then quantum mechanics presents some extra challenges associated with knowing the state. And to this, the wave function postulate says that the quantum state can be represented by a mathematical function called the wave function, which must satisfy some properties. So that's the essence of what we have discussed. But now you might say, cool, I understand that the wave function is meant to represent the state of quantum system, but how does this wave function actually account for all the unique features of the quantum world? So, firstly, the wave function can be used to predict the time evolution of the quantum state. Let's take a second to understand this correctly. Remember that in quantum mechanics, we are interested in the probability distributions of observables rather than the values themselves. So what we are saying here is that the wave function can be used to predict how these probability distributions change with time. Mathematically, the time evolution of the wave function is modeled using a differential equation, which is known as the Schrödinger equation. Now, dealing with probability distributions brings up two important questions. What values of observables are actually possible? For example, an electron in an atom can only have very specific, discrete energy values. What are these values? This question can be answered using the wave function in conjunction with the measurement postulate of quantum mechanics, which we'll cover in the 4th video in this series. Secondly, you might expect certain values to appear more often than others. This begs the question, what is the expectation value of the energy or any other observable for that matter? This is yet another question that can be answered by our wave function. For this we can use the expectation value postulate, which we'll also cover. So far, we have seen that the classical state of a system can be represented by the position and momentum of a particle, and that the quantum state behaves differently and must therefore be represented in a different way. For that, we use the wave function. Then, we discussed the properties that a valid wave function must have. Lastly, we quickly discussed a few ways the wave function addresses the probabilistic nature of quantum physics. I told you guys that the wave function can be used to determine how the quantum state will change with time. It can also be used to find the expectation value of an observable, as well as the state of all possible values that an observable can ever take on. Thanks for watching. I'll see you in the next video.